My name is Srikanth Sethi. I work in the performance engineering group at VMware. And I'm really delighted to have with me Gabriel, who is the key architect behind all the new features that we added to vMotion in vSphere 5. So this is the usual disclaimer. So let me quickly walk through the outline of the presentation today. So, but before I start, as everyone knows here, vMotion is one of the most popular features of vSphere. Customers have been using the technology since the earliest versions of ESX. In fact, as Paul pointed out in his presentation yesterday, millions and millions and even more millions of vMotions have been performed to date successfully. Even so, we do get occasionally questions from customers asking how the technology works, what is the performance impact of vMotion on their specific set of applications, what they can do to improve performance, and so on. So today, Gabriel is going to demystify this vMotion technology for us. He's going to, in fact, give us a quick timeline tour of how the technology evolved over the last few releases of vSphere. And he'll also give us the rationale behind why we added all the new features in vMotion. Okay, and you'll see later in the presentation that some of these features give us phenomenal improvement in performance. In one of the cases, we've seen a performance improvement by order of 5x. And so what we're going to do is, after Gabe's overview, I'm going to consider a large domain of tier 1 applications and different workloads and try to quantify the performance improvement from all these new features. And I'll also try to emphasize some of the key points so you can apply them in your own environment. Okay, and I'll also share with you some of the best practices you need to keep in mind and some of the common pitfalls you need to avoid to get the maximum benefit out of all these features. And finally, we'll have some conclusions. And we'll try to make sure you'll have at least 10 minutes of Q&A at the end of the talk. Okay? So.
All right. So I imagine pretty much all of you are familiar with what vMotion is. vMotion is our feature that lets you move a running virtual machine from one ESX host in your cluster to another ESX host in your cluster, leveraging shared storage and shared VM network connectivity. But I'd also like to talk about a little bit how it works, the underlying mechanisms, and how we actually move a VM state from one host to another over your vMotion network. Importantly, a vMotion is transparent to the guest operating system running inside the VM. The guest has absolutely no insight into the fact that it's being vMotioned. The VM is simply running somewhere, and then the next moment it's running somewhere else. The guest doesn't have any idea it was moved. In general, vMotion is an invaluable tool to admins, as I'm sure you all know. It gives you a great deal of flexibility. It means your VMs are not tied to any particular physical host. It allows you to do vMotions to balance load across clusters. Say one host has more resources than another, so you move the VM to the other host. Or you can perform maintenance by moving VMs off of hosts. And we have a lot of features built on top of vMotion that leverage these underlying features. For example, DRS uses vMotion to load balance. It looks for imbalance in cluster resource utilization and moves VMs accordingly. We have DPM, which moves around VMs, or moves VM off of hosts that have, well, when your cluster has spare capacity, it moves VMs off of hosts so it can power down individual hosts and save you power. And then there's FT, which uses vMotion to kick off new secondary VMs. So vMotion is the launching pad for creating new secondary FT VMs. So how does vMotion work? Well, when you're doing a vMotion, you have to move your source VM to the destination host, of course, but your VM has a lot of state associated with it. Your VM has virtual processors, it has virtual devices, it has associations with the physical network and VMDKs, or physical storage at some level or another. So we have to be able to move this state somehow from the source host to the destination host. The majority of this virtual device movement is handled by something called the checkpoint infrastructure, which is something built into ESX, and it's used by a bunch of other features, including suspender zoom. The idea is that we step over all of your VM's virtual devices and serialize their state into an opaque checkpoint opaque blob that we can then transfer from the source host to the destination host, deserialize that state at the destination VM, and then we wind up with the same virtual device state as you had at the source VM. But it's not quite that simple, because your VM also has associations with physical resources. For example, your network, your physical network, or your VMDKs, or physical storage. So we also have to transfer those associations. We do disk, of course, as you are probably aware, is kind of easy for us. We require that when you vMotion a VM across two ACX hosts, those hosts have to share all the common storage that is used by that VM's VMDKs. So whatever storage that VM is relying upon needs to be accessible to both source and destination host. And when we're doing the vMotion, all we have to do is release ownership of those VMDKs on the source host, open the same VMDKs on the destination host, and we've transferred your storage. Pretty easy. The network is handled similarly because we require that your VM is not changing VM networks during vMotion. So all we have to do is, after deserializing your VM's device state on the destination, we send a reverse ARP to your switch so it knows that the VM is moved and where to route the new packets. But we haven't talked about the most interesting part of vMotion, which is how we handle your VM's memory. Now, a very naive implementation of vMotion, a very simple version, which would work, would be to simply decide you want to do a vMotion, quiesce the source VM. That involves waiting for in-flight I/O so we can serialize its state, compute that device checkpoint, send that to the destination, and then send all of your VM's memory to the destination host as well. I mean, your VM is quiesced, so it's not going to change any memory or device content. And this would work just fine, except if we did this, let's consider a 64 gigabyte VM. If you've got 64 gigabytes of memory in your VM, and we quiesce it before sending all of that memory to the destination host, that could take quite a while. I mean, if you've got a 10 gig network, sending 64 gigs of memory could take about 50 seconds. I don't think you'll be very happy if every time you vMotion, your VM freezes for 50 seconds. I mean, you'll certainly lose network connectivity to the VM. Users will complain. It just won't be a very happy situation. So we don't do that. Instead, we take the approach of letting your VM run for the vast majority of vMotion. So what we do is we want to iteratively copy your VM's memory, because as your VM's running, it's going to be changing its memory. So what we do is take a pass over your VM's memory, copy all the contents of your VM's memory from the source host to the destination host, and after that full pass copy is completed, we go back and look to see what's changed since we completed that first pass copy, because your VM has been running the whole time and dirtying memory, right? So we go back and make another pass over memory, copy whatever's changed. And then we do it again. We go back, see what changed in that previous copy, copy all that. This is called iterative precopy. So let's look at an example of how this works. Let's take a 40 gig VM. We copy all the content from the source host to the destination host. As we copy that memory, the VM is dirtying pages. So in this case, the orange or red blocks are dirtied memory. And let's say while we were taking that first pass of the 40 gigabytes of memory, the VM was running, so it dirtied another 20 gigabytes of memory, which means we have to recopy those 20 gigabytes of memory. So in the next pass, we copy those 20 gigabytes. And while we make that pass of memory copy, the VM dirties another 11 gigabytes of memory. So that means we have to make another pass, copy that memory, and while we do that, the VM is dirtied yet another 5 gigabytes of memory. And we make another pass and copy that. At this point, let's just say for the purpose of this slide that we're done, in reality, the idea behind precopy, since we're making forward progress here, is to just keep going until no outstanding memory remains. So we're just iteratively copying your memory over the network. We're transferring it faster than your VM is changing it, so we eventually converge to no outstanding memory. This is iterative precopy. Let's talk about that in slightly more detail, because Sri will be talking about the performance implications, so it's important that we understand all the subtle implementation details. So the first phase of iterative precopy performs a little optimization. When you make that very first pass of memory copy, you don't actually want to copy all of your VM's memory, because that would be pretty inefficient. What we do instead is decide which pages we consider cold pages, or pages that are not likely to change anytime soon, because the pages that change least frequently are the ones we want to send earliest, right? Because then we won't have to resend them later because they'll never change. So in that very first passive precopy, the trace phase, or light heat phase, we spend that just copying our cold pages and also installing traces on your VM's memory pages. Traces are the function we use so that we can monitor when your VM changes its memory. It just means once we've installed a trace, we'll get a callback in the kernel whenever your VM dirties a given memory page. So that very first phase, we trace all your memory and send the cold pages. After that, we go on with normal precopy. We've completed the cold, or the trace phase, so now we just copy all pages as we see that they have changed since the last iteration. So it's just precopy as I described it before. And then we proceed to the switchover phase. The switchover phase is the part where we quiesce the source VM, wait for its in-flight hypervisor level I/O, serialize the device state, send that to the destination host, deserialize that state. All in all, that process generally takes about half a second. This is significant because during this half a second, your vCPUs are not executing guest instructions. We had to quiesce the source VM so that we could compute its device state. So during this switchover time, you will notice some sort of workload impact because, as I said, we're not actually executing guest instructions. Fortunately, half a second for switchover is brief enough that TCP's reliable transmission protocol guarantees that you won't actually lose network connectivity, you won't notice any significant packet loss. The catch is if you're using UDP, you might notice the packet loss here and there because UDP is not reliable, therefore in the half second, you could lose some packets there. But in general, that half second should be largely transparent. So how does this all play together? Let's take a look at how ESX41 worked, or CAL next. So as I said before, the first step is you precopy memory. You quiesce the source, transfer device state, deserialize the device state of the destination, and resume the destination. There's a trick here, though. Iterative precopy only works if we're iteratively making forward progress. So as I said, we're transferring memory over the network as your VM is dirtying it, or slightly after your VM is dirtying it. But the requirement is that we eventually converge down to no outstanding memory. I mean, that's the whole point, right? But what happens if your VM is dirtying memory more quickly than we can send it over the network? Precopy won't converge. That's called a precopy convergence failure. We have to handle that somehow. We've handled it differently in every release of ESX. ESX5 is an entirely new implementation, which I'll talk about in a second. But ESX41 had this thing called RDPI, or in marketing literature, quick resume. The idea was you let precopy fail to converge, and you proceed with switchover anyway. So your VM is at the destination host, we've deserialized its state, and we actually let it start running without all of its memory having been received. This means that your VM is executing guest instructions, and it could well decide to touch a bit of memory that it hasn't yet actually received over the vMotion network. So though we have the source in parallel copying all the remaining memory from the source to destination, the destination's running. So upon finding one of these missing memory pages, we use what's called a remote page fault. This means that whenever the VM touches any given page that it hasn't yet received over the network, it sends an RPC to the source host to request the page content. We send that back to the destination, map it into the VM's memory, and let the VM start running again. This is great. It means performance is improved vastly compared to other approaches, especially say the naive approach. The problem, though, is that if we manage to, or rather, if precopy failed because your VM is very aggressively dirtying memory, it's possible that the vast majority of your VM's working set could be missing in the destination, which means as soon as the destination starts running, it has to page fault a ton of pages, which means the vCPUs are constantly switching to the kernel to do remote page faults. So performance can be impacted, and Sri will talk about that in more detail. But because of the performance implications, we decided to switch to a different approach that more optimized for VM performance. So ESX5. We have made a number of improvements that just across the board improve vMotion performance and also VM performance during vMotion. Both, of course, are very important factors for all of you. The first thing we've done is improve the performance of write traces. As I said, those are the mechanism we use to monitor whether your VM is dirtying pages or not, and the initial install of those write traces during the trace phase can be noticeable in terms of VM workload impact. But we have optimized the trace install path significantly, so these days you shouldn't really notice an impact in VM workload performance during the trace phase, and Sri has concrete examples of this later. We have just generally optimized the vMotion transmit and receive network stack implementations. So while we were very close to saturating 10 gig line rate in ESX4.1, we are pretty much there in ESX5. We regularly see over 9 gig throughput on our 10 gig NIC testbeds. And in addition to that, we have implemented support for multiple vMotion VMK NICs. So in previous releases of ESX, you could only have one vMotion VMK NIC per host. Now you can have as many as you want, well, up to 16. Which means that if you've got, say, a host with 3 10 gig NICs and you aren't using that bandwidth for something else for some reason, then you can dedicate them to vMotion. And we will transparently load balance all our vMotion traffic over as many vMotion VMK NICs as you give us. So if you give us 3 10 gig NICs, we will use them for vMotion. Even if you're just vMotioning one VM at a time, we'll still load balance all that traffic over your NICs. Or of course, if you have multiple 1 gig NICs in your host, I mean, there are plenty of cards with those, 5 NICs on them. You can dedicate 5 1 gig NICs or a 1 gig NIC and a 10 gig NIC or whatever you want to vMotion, and we'll transparently load balance our traffic over all that. Perhaps most importantly, though, we've implemented something called SDPS. SDPS is our answer to RDPI or Precopy convergence failures in ESX5. SDPS kind of ditches the entire approach RDPI took of trying to recover from a Precopy convergence failure. Instead, what we do is decide that we really want Precopy to converge. So let's make it converge. What we do is monitor your VM's we monitor your VM's dirty rate and our vMotion network transmit rate. And if we observe that your VM's dirty rate is exceeding your vMotion network transmit rate, then we will inject microsecond delays into the execution of your VM's vCPUs. What this means is we will, during vMotion, disrupt the execution of your VM's workload just enough so that our network transmit rate will climb above your VM's ability to dirty memory. Now, keep in mind, this only takes effect in cases where Precopy convergence would have failed before. So any sort of performance impact of SDPS is strictly limited to the cases where RDPI would have kicked in before. So really, if you have to reason about SDPS performance, you have to also consider how RDPI would have performed in ESX4.1. The important detail here, though, is that SDPS leaves us in control of how much we slow down the VM, whereas RDPI, your VM could get stuck doing all these remote page faults. So it gives us much more control. It means that during vMotion, we can still guarantee some whatever level of VM performance is required. And it just means that generally, now we don't have to worry about Precopy convergence failures, because by definition, with SDPS, Precopy will always converge, regardless of your vMotion network transmit rate. So nowadays, the vMotion process is much simpler. We will Precopy your memory with SDPS. Precopy will always converge. We will quiesce the VM, compute its device state, send that state to the destination host, deserialize that. We will transmit whatever memory was remaining at the end of Precopy. But since Precopy converge, that should be on the order of not many pages. We send that in probably a few milliseconds. And then we can let the destination VM run, mark the vMotion complete, free the source VM resources, and you're done. So now I will hand this off to Sri to talk about the performance impact or improvements and how this works in workloads.
Now let's just take a quick look at some of the performance data. So this is the test configuration that we used. As you see here, we used 2 Nehalem hosts, and each of the hosts has 3 NICs with it. We used 1 10 GB NIC for client traffic, and 2 of the 10 GB NICs were used for vMotion traffic. So how do you measure vMotion performance? So of course, there are a number of metrics that you can use. For instance, you can measure how much CPU and memory resources you need to do the actual migration. You can also measure the total time you need to complete the migration. And if you're a customer who has some real-time applications, they'll definitely focus on the switchover time, because that's the time during which we quiesce the VM, which will enable us to switch over the VM from the source to the destination host. And finally, and most importantly, you can also measure vMotion performance by actually measuring the performance impact of vMotion on guest applications which are running inside the virtual machine during and after vMotion. So So there are different metrics, and all these are very important metrics. But based on the context of the workload, sometimes a few metrics are much more appealing than other metrics. So what we've done is we consider different workloads, but based on the context of the workload, we try different metrics. So again, how do you characterize performance? Each customer has a unique workload, and all these workloads have a unique characteristics. So what we have done was we considered a large domain of tier 1 applications that consisted of web servers, messaging servers, database servers, and so on. And all these workloads have a different characteristics. For instance, web server is extremely network intensive, and Exchange workload is extremely memory intensive. And as far as the database is concerned, as we all know, it's very CPU, memory, and storage intensive. And finally, apart from all these tier 1 applications, we also considered a cloud deployment scenario, or a VDA deployment scenario, which is characterized by a very high consolidation ratio. So I'm going to give you more details about all these workloads as I present the performance numbers. So how do we measure time? As Gabriel mentioned, vMotion has different phases. The first phase is a guest trace phase, where we install all the traces on the guest memory. And then there's a Precopy phase, where we iteratively transfer all the memory to the destination host. And finally, we have a switchover phase, where we suspend the VM and then enable the switchover to the destination host. So the time reported under the virtual center server doesn't give you that fine-grained information about all these phases. And one more important thing is the time reported by the VC not only includes the actual time during which we complete the migration, but it also has various other management latencies. So all these management latencies have absolutely no bearing on guest performance. So to get this precise information, what we've done was we used VMware sysinfo interface as well as the VM kernel logs. So each vMotion has a unique ID associated with it. Okay, and we refer to it as migration ID. And this migration ID happens to be the same on both source as well as the destination host. Okay, so here I give some example how you can obtain this migration ID using the VSI interface. The only caution here is the VSI interface keeps changing across vSphere releases. So the example that I gave you here may not work possibly in the future releases of vSphere, but it should work on vSphere 5 and the prior versions. So once you have this migration ID, all you need to do is refer this migration ID in the VM kernel logs on the both source as well as the destination host. And then you'll see lots of valuable information, such as all the information about all the different phases and the statistics and so on. For instance, in this particular example, we have about 3 phases. Okay, let's see, this is not working. We have 2 phases actually. Can you see? Okay, yeah, I can see it. So we have 2 phases here. And we also report network bandwidth used and so on. So you'll find basically tons of useful information. Most of the customers don't really need all this information, but just in case if you want to really understand what's going on, you can use this approach to find more information. Okay, so as a first case study, let's look at web server performance. So to understand the web server performance, we used a workload called SpecWeb 2005. It's an industry standard workload defined by the spec committee. And in fact, this is the workload used by almost all the hardware vendors when they publish their performance numbers. So basically this workload, it represents a typical web architecture where you have the clients, web server, and a backend application server. And the performance here, what we measure is the total number of simultaneous browser sessions that web server can handle while still meeting all the quality of service requirements. Okay, and as you can see, we also configured the benchmark so that the clients report fine-grained performance data. So all the clients are reporting the performance data every 2 seconds, which basically helped us quantify the application slowdown during the entire vMotion. So our objectives are again, we wanted to understand what is the total migration time, And we also wanted to understand what is the impact on vMotion on the web server performance during the vMotion. So here, let's just focus on the total duration. What we are comparing here in this figure is the total duration that we needed to complete the vMotion on both vSphere 4.1 and vSphere 5. And as I said, we were running at 12,000 browser sessions, which generated as much as 6 Gbps client traffic. So obviously, this is a very heavy-duty VM with about 6 Gbps web traffic. Even then, we've seen that there's not a single connection drop. And we've seen a significant improvement in performance from vSphere 4.1 to vSphere 5. And our analysis basically showed that the improvement was mainly because in vSphere 5, the vMotion was able to more effectively use all the 10 GB bandwidth. Okay, now that we looked at the total duration, we also wanted to understand what's the impact on the application performance. So here, what I'm plotting here is the time good, which is the total number of browser sessions that are actually meeting the quality of service requirements. Okay, so so as you can see, we have this is a ramp-up time, and we see a small dip here. Basically, that's basically signifies the beginning of the steady state, during which we see a small dip because we're clearing all the statistics, and then this is the start of the steady state. And as you can see, during the steady state, we had 100% of the users meeting the quality of service requirements. But as soon as we started the vMotion, we saw two noticeable dips. The first dip was during guest trace phase, because as Gabriel mentioned, tracing all the memory pages can have some impact on performance. And finally, we've seen one more dip when we had to quash the VM and do a switchover. And one more interesting thing you'll notice is the actual sessions that are submitting the request is 2750. I mentioned that we were using 12,000 users, but you see the difference mainly because the benchmark has a think time component to it. So even though they had 12,000 sessions, the actual session submitting the request is 2750. But the important thing was there was not a single network connection dropped. And even when we were doing a vMotion of this heavy-duty VM, the performance was pretty reasonably good, And so let's now take exactly look at running the same workload, but running vSphere 5. Once again, we can see that that ramp up quickly started, and then there was a start of the steady state here. And during the steady state, all the users were meeting their quality of service requirements. But as soon as we started vMotion, about 1 or 2 minutes into the steady state, we saw a very, very minor dip during the tracing phase. This is because we made lots of improvements to reduce the impact of memory traces. And then finally, we've seen one small dip during the switchover phase. One more important thing was the time to resume to the normal level of performance was about few seconds better than what we've seen in 4.1. So again, there are lots of improvements across the board. You see, we reduced the total duration. And even during this shorter duration, the impact on the application was much minimal. So far I've been talking about all the vMotion performance using 10 GB NIC. So let's see what happens when you use a 1 GB NIC. So here we wanted to understand the vMotion impact or vMotion performance on both 1 GB NIC versus 10 GB NIC, and on both vSphere 4.1 as well as vSphere 5. So we used 3 test scenarios. As you can see, we have one idle VM, a moderately loaded VM, and a heavily loaded VM. The heavily loaded VM scenario was exactly the same as what I've been talking in the previous slide, but I also added a couple of scenarios. So let's just take a look at idle and moderately loaded VM scenarios. So, so basically what we're seeing, I have about a few data points here. So what I'm comparing, let's say here is for the idle VM, I have 4 data points. So I'm comparing 1 GB versus 10 GB on 4.1, 1 GB versus 10 GB on vSphere 5 for idle VM scenario. And same thing for moderately loaded VM also again have 1 GB versus 10 GB, 1 GB versus 10 GB. As you can see, in both the scenarios, the improvements were phenomenal. The improvements were in the order of 8 to 10x, and mainly because we're able to effectively saturate the 10 GB bandwidth. So that brings us to the very first key takeaway point here. So if possible, you should seriously consider switching to a 10 GB vMotion network here. And now let's also consider a heavily loaded VM scenario. Once again, we see significant improvements in performance using 10 GB versus 1 GB. As you can see here, we had 12,000 users, and the performance dropped by a factor of 10 or so on vSphere 5, and it's same thing on vSphere 4.1. But you'll see one interesting fact note here is we marked this data point on at 1 GB as in a gradient shade. It's because we ran into a very interesting scenario. As Gabriel mentioned in his, during his overview, we ran into this pathological scenario where the VM was dirtying its memory so fast, vMotion was not able to actually transfer all these dirty pages on the 1 GB network. And the 1 GB obviously has a 1 GB bandwidth. So, and the VM was churning out these dirty pages so fast, vMotion was not able to actually transfer these dirty pages fast enough on a 1 GB network than the rate at which VM was dirtying the memory pages. So, so what happened? So we had to actually suspend the VM, copy all the dirty pages, and then do the switchover. So obviously the vMotion completed, but it had some impact on the performance. We've seen some network connection drops and so on. So, but but we ran exactly the same scenario on vSphere 5, and obviously since the workload is the same, we ran into the same pathological scenario. We were not able to transfer the dirty pages fast enough on a 1 GB network than the rate at which the VM was producing all these dirty pages. And thankfully, we had this new feature called STPS, which Gabriel talked about. So what this feature basically kicked in, and what it did was it basically injects microsecond latencies into the VCP execution. So what it means is it just slows down the VM just enough so the transfer rate can catch up with the memory modification rate. So thanks to this feature, what actually happened was we haven't seen a single connection drop. So again, what we are guaranteeing here is the vMotion vSphere 5 will never fail due to the Precopy convergence issues. So even if you have a pathological workload, or even if you have a limitations in your network infrastructure, you will see that vMotion will always converge. Of course, we're not guaranteeing that vMotion will never fail. You can always, pull out your network cable. vMotion can fail. So, but what we're guaranteeing here is, even if you have pathological workloads, or even if you have limitations in network infrastructure, the vMotion should progress very smoothly. So I guess having already looked at the web server data, let's look at database performance also. Here, as you can see in the slides, we're using a DVD store. It's an open source DS2 benchmark, and performance is measured in terms of orders per second. And we also, once again, enabled fine-grained performance tracking, so the clients report the performance data every 1 second. And for the test scenario, we used a single VM as well as multiple VM scenarios. And each VM was running SQL Server, and I was hosting a 50 gigabytes of database. So in a multi-VM scenario, the total size of the database was about 100 gigabytes. And once again, the objectives were the total migration time, and we also wanted to understand performance impact on the database server during and after vMotion. So, so here, let me also quickly talk about the new feature that we introduced in vSphere. Gabriel already mentioned it. So we are we are basically enabling you to use multiple NICs for vMotion traffic. So if you configure multiple NICs for vMotion, vMkernel is going to transparently load balance all the vMotion traffic onto all these vMotion NICs. So let's take a quick look at the performance. So once again, we are comparing the performance of vMotion, the total duration, on vSphere 4.1, vSphere 5. And for vSphere 5, we have two data points using 10 GB NIC, one 10 GB NIC, and the second data point is using two 10 GB NICs. So even if you don't use this particular feature, you can see that the improvement was pretty good. We've seen about 35% improvement from just moving from vSphere 4.1 to vSphere 5. And when we enable multiple NICs, the performance improvement was by a factor of 2. So, and we've seen exactly the same performance improvements even on using a multi-VM scenario also. There was about 35% improvement using one 10 GB NIC. And when we used two 10 GB NICs, the performance improvement was more than a factor of 2. I guess the key takeaway point here is even if you have a single VM that is subjected to vMotion, VM kernel is still going to transparently load balance the vMotion traffic onto multiple NICs. So I guess this is going to be a very useful feature when you have a monster VMs. Let's say you have a 256 GB VM or a terabyte size VM. Having multiple NICs will definitely improve the vMotion performance. So once again, I wanted to also take a look at the performance impact on the database server during and after vMotion. So again, once again, I have two graphs here depicting vMotion performance or the database server performance during the entire vMotion. And again, as you can see here, during the steady state, we had about 350 operations per second. And on vSphere 4.1, we saw two noticeable dips, both on during the memory trace phase as well as during the switchover phase. In comparison, thanks to all the improvements that we made to memory traces, in vSphere 5, the dip during the memory trace phase was very, very minimal. And another interesting thing you'll notice here is the throughput was never non-zero. It's because the switchover time was just less than a half second. And since we are measuring this performance, or we are tracking the performance at 1 second granularity, we've seen that the throughput was never zero. And another important thing is the time to resume to normal level of performance was about 2 seconds better than what we've seen on 4.1. So once again, the improvements were all board. We reduced the duration, we reduced the impact on the application performance, and also the time to resume to normal level of performance was also much improved. So I think we spent enough time on all the tier 1 applications. So I also wanted to consider another interesting workload scenario, which is VDI. VDI is virtual desktop infrastructure. So I guess most of the people here already know about it. For those of you who don't know, VDI is a pretty cool solution. It basically replaces your physical PC desktop with a virtual desktop. And this virtual desktop is basically running inside a virtual machine on a remote vSphere host. But it gives you exactly the same and complete and isolated PC environment, just like your traditional desktop. In fact, VMware has a VMware view which provides this solution. And one more interesting thing is the VDI and cloud deployment both share lots of unique characteristics. For instance, both have very high consolidation ratios. Typically, you'll have like hundreds of small to medium-sized VMs consolidated on a single host. So in the tier 1 applications that we talked about, we usually talk about 1 VM or 2 VMs, but very large VMs, right? But here we are talking about lots of VMs, but small to medium-sized VMs. So here also we wanted to really understand what goes on. Because the administrators of these environments typically do a host maintenance operation. So basically what they do is if they need to bring down a host for, let's say, a hardware upgrade or a firmware upgrade, all they need to do is they need to initiate this host maintenance operation. So even if you have these hundreds of VMs running, the DRS will automatically kick in and migrate all these hundreds of VMs running on this host to all other hosts running in your cluster. So it just happens at one click of a button. So for these administrators, obviously the performance of host maintenance operation is very, very important. Because obviously you don't want to do these migrations one at a time. You want to be able to use all the resources you have, but you want to be able to evacuate all these VMs as fast as possible. Once again, we looked at the performance data for evacuation on both vSphere 4.1 and vSphere 5. And as you can see, we have seen phenomenal improvement in performance. So the total time to evacuate all these VMs dropped from about 11 minutes to just about 2 minutes. And you may really, many people may not really actually believe this data, and I want to show why we made these performance improvements. Here what I'm looking at is, I'm looking at the network utilization during the migration scenario. So we support up to 8 concurrent vMotions at a given time. So we had about 64 total migrations that were needed, right? So, so that basically turned into 8 different phases. And in each of these 8 phases, we had 8 vMotions going on. And during each phase, as you can see, we were able to actually use about 8 Gbps bandwidth. Okay. So we were able to actually use a bandwidth very effectively, but unfortunately, between all these phases, the network usage remained idle because of all the management latencies. So obviously, it's not optimal, and we made tremendous improvements here. And this is how the network utilization looks like on vSphere 5. You can see there's no longer that bimodal distribution. We were able to actually use the 10 GB bandwidth very effectively, and we pretty much eliminated all the management latencies. So what does it mean for the admins? It just means when you do this host maintenance operation, you don't really need to take your coffee break. You don't really need 10 or 15 minutes of coffee break. Before you fetch your cup of joe, it should be done. It just takes about a minute or 2 minutes, even if you have hundreds of VMs running on your host. So, I think we looked enough at the performance data. I also want to sum up all this, sum up some of the best practices based on all this performance data. So if possible, if you have a 10 GB NX, I think it's a good idea for you to switch to a 10 GB vMotion network. And if you want to further speed up vMotion duration, you should consider using multiple NICs. And if you plan to use multiple NICs, we suggest you to place all these multiple NICs under the same vSwitch. And for each of the vMotion VMK NIC, use a different VM NIC as the active VM NIC, and you can mark rest of the VM NICs as standby. Okay, so the idea is, let's say if one of the active VM NICs fails, vMotion is going to transparently switch over to the standby VM NICs. And if you're very, very concerned about vMotion performance, let's say if you have some real-time applications and so on, and you're really worried about the performance of the suspension time, we suggest you to place all your swap files on a SAN or a NAS. Because if you place all your VM swap files on a local storage or on a SSD cache, it can have some impact on performance. Usually, it's not it's not something you need to worry. But if you have some real-time apps and you're really concerned about vMotion performance, we strongly suggest you to consider using a SAN for placing all your swap files. So vNuma is a new feature that we introduced in vSphere 5. You must have already heard about it during other presentation. So basically, vNuma exposes the NUMA topology of the physical host to the guest. So once this topology is actually set when the VM is powered on. And once you power it on, this topology won't change. So the problem is, if you now, let's say, migrate this VM to a host which has a different NUMA topology, the performance may not be optimal. So just bear that in mind. So when you have the ESX clusters, make sure all the hosts within the clusters have the same NUMA topology, especially when you're using a vNuma feature. And finally, when you're using CPU reservations, we suggest you to leave at least some spare CPU capacity at the host as well as at the cluster level. And because if you don't have enough spare capacity at the cluster level, DRS may fail. And at the host level, all we ask you to do is just leave 30% of a CPU, not the 30% of the entire CPU capacity of a host, but just 30% of a single CPU core on a host. Because we opportunistically reserve that amount of CPU when we do a vMotion, because vMotion needs some CPU resources. And even if we fail to get that reservation, we still do vMotion, but it can impact vMotion performance. So that brings us to the conclusions. As you've seen, vMotion has a number of new features and enhancements. We enable multiple NICs for vMotion traffic, and we effectively utilize the 10 GB bandwidth. And we also have a new feature called Metro vMotion. Unfortunately, I didn't have time to talk about Metro vMotion, but the vMotion in vSphere 5 is latency sensitive. So we not only give you better performance on long latency networks, but we also increase the round trip latency limit from 5 seconds to 10 seconds, 5 milliseconds to 10 milliseconds. Finally, even if you have some pathological workloads, many times, we run into these customers who are really hesitant to move to, virtualized infrastructure because the executives may want it, but the people are, hesitant to, change their ways. And they try to create these pathological workloads where they just try to show, performance of vMotion is bad. And for those people, we have the answer now. Thanks to the STPS feature that we have, vMotion will progress much more smoothly than ever before. And I think if I have not emphasized enough, we have lots of dramatic improvements in vSphere 5 for vMotion. And again, the improvements are in number of areas. We reduce the duration, we reduce the impact on the application performance, we ensure the vMotion progresses smoothly. And I know this presentation was right after lunch, so some of you might have dozed off, but and if you've just woken up, and you haven't really heard about all these features, all you need to do is just upgrade to vSphere 5, and you'll get 35 to 30% minimum improvement in performance. Okay, you don't need to use any of the features, but because most of the features are all transparent. But if you somehow manage to keep yourself awake and use some of the features like multiple NICs, you can dramatically cut down the vMotion durations by at least a factor of 2x or 5x, depending on the context of the workload. So, so we have some time, I think, for Q&A now, and please do fill the surveys.